Hello and welcome friends. This video is to discuss about Opamp, okay, which is a very important electrical circuit component. So this video is dedicated to Opamp, which stands for operational amplifier. In short, Opamp. So this is a very important circuit component in many electrical and electronic circuits. That's what we are going to discuss. Now, it is okay. Before telling anything else, let me just tell you that it is drawn as a triangle in all electrical circuit diagrams. Okay, so and this has two input terminals and one output terminal. The two input terminals are given the names as plus and minus, also known as the non-inverting and inverting terminals, but it's easier to remember the plus and minus name. Okay, so there are two input terminals formerly known as inverting and non-inverting terminals, or minus and plus terminals, and one output terminal. So this is the output side, this is the input side. Two inputs and one output. Okay, apart from that, this also has power supplies. So we connect one power supply with a positive supply voltage plus V supply, and the other terminal with a minus V supply. Okay, so this is not a passive device like a resistance or inductance, capacitance. It's not a diode. So those are all passive devices. Okay, this is an active device. By that I mean, for this device to work, it needs some power supply. This is it's an intelligent device. It, in a sense, why do I say so? I will see soon. So it requires an power supply, power input. This is actually an integrated chip, IC, integrated circuit. Okay, which has two inputs and one output. What is there inside this IC? It's complicated and we are not going to discuss about that, but we'll see that the functional behavior of an op-amp is very simple. It has only two inputs and one output. And how does it work? It works based on this principle, very simple principle, which says, okay, let me denote the voltage given here at plus terminal as V positive Vp, at this voltage as Vn, V negative. Okay, now the op-amp works based on the principle that if Vp is greater than Vn, then output is positive. If positive input is higher, then the output is positive, and this is equal to plus V supply. And if Vn is greater than Vp, then output is equal to minus V supply. So that means, say I connect a battery. The other end is grounded. This side is 2 volt, and this one I connect it with a different battery. The other end is grounded, and this side is at 3 volt. Okay, so 3 volt is higher than 2 volt. That means Vn is higher than Vp, and when Vn is higher than Vp, the output should be minus V supply. right? And similarly, if we make, say, Vn equal to 1 volt, say if I give a 1 volt supply and Vp equal to 2 volt, so if I connect a 2 volt supply here, then output is equal to plus V supply. If, say, this V supply is 12 volt plus 12 volt here, and here this is equal to minus 12 volt, then this output in this case, when Vp is higher than Vn, will be plus V supply, that is plus 12 volt. It is very simple. So what does this op-amp do? It compares the two input, which one is higher. If this one, if the plus one is higher, the output is equal to plus supply voltage, and if this one is higher, the output is equal to minus supply voltage. So it compares two inputs. So that's why I said, and the op-amp is an intelligent device. It can compare between two voltages, and accordingly it can tell us which one is higher. If this is higher, the output will be positive, and if this is higher, the output will be negative. So that's why the op-amp, I mean this behavior of op-amp is also called as a comparator. Comparator. So it compares two inputs, and if this is higher, the output is positive. If the minus input is higher, the output is negative. As simple as that. Now the same thing what I just said now can be also demonstrated with a graph. Okay, so I will draw a graph, input versus output graph for this op-amp. So x-axis as usual will be the input, will represent the input, and the y-axis as usual will represent the output voltage. That we call this VO for V output voltage. And there is a problem that there are two inputs, but I have only one x-axis. So how can I represent two inputs with one x-axis? So I will use a trick. I will represent the value of Vp minus Vn as my x-axis. That is, x-axis represents the difference between these two inputs, Vp minus Vn. So this difference, for this case, when so Vp minus Vn is in this case 2 volt minus 3 volt, which is minus 1 volt. So that we will represent along the x-axis, Vp minus Vn. Now we know, as we have said, that when Vp is greater than Vn, okay, when Vp is greater than Vn, that means Vp minus Vn is positive. So this implies then Vp minus Vn is greater than 0. Okay, if Vp greater than Vn, then Vp minus Vn is greater than 0. So that is represented by the right side of x-axis, where Vp minus Vn is greater than 0. And this side, Vp minus Vn is negative, which means this condition Vn is greater than Vp. So here Vn is greater than Vp. So on this side Vn is greater than Vp, and on this side Vp is greater than Vn. Now we know that when Vp is greater than Vn, the output is equal to the positive supply voltage. So this value is plus V supply. So whenever this is, Vp is greater than Vn, it's positive, and it goes on like this. On this side, the output is negative and is equal to minus V supply, because Vn, the negative input, is higher than the positive input. It's very simple, nothing complicated. Okay, and so this point represents where Vp minus Vn is equal to 0. That means Vp is equal to Vn. So here Vp is equal to Vn. and the region near this, so this is where, so this region, see this region, something like this, is where Vp is very close to Vn. They're approximately equal. One can be slightly higher than the other, or the other one can be slightly higher than the one, but they're very close to each other. Now what happens in this region? In this region, the voltage, the output voltage increases slowly from the negative value to the positive value, something like this. Exact shape of it is not important, but it slowly and continuously, smoothly increases from here to here. Whether it's a straight line, whether it's a curved line, that's not important, but it increases like this. Okay, yeah, and this gap, okay, this gap, let me give it a name. Let me give this the name of resolution. Okay, what does this word resolution means? So it's a measure of how good the op-amp is. If the op-amp is very good, then that means it can compare and distinguish between if even slight amount of difference between Vp and Vn. So if the difference is even very small, then it can decide which one is higher and which one is lower. If the resolution is poor, then it cannot distinguish, cannot decide what to do when Vp and Vn is very close, because you see that this region, the output is negative, so the op-amp is confident, the op-amp knows that the negative terminal has a higher voltage than positive terminal. Here the op-amp is confident that the positive terminal, positive input terminal has a higher voltage than the negative input terminal. Here the op-amp is not that confident, it doesn't know exactly what to say, because the two inputs are very close to each other. So I say that's why I say the op-amp, you can think it's an intelligent device, it's a smart device. But in this region it cannot say confidently which one is higher, it cannot decide which one is higher, and the output therefore changes slowly from the negative value to positive value in this region, but it's never fully positive or fully negative or fully positive, because it's not that confident about the difference between the two inputs. Okay, so this is the property of an op-amp. I'll call this property as the property 1, the first basic property of an op-amp. And this curve is also called as a static characteristic. Now the word characteristic is synonymous to property, and why is it called static? Let's not discuss that now. Okay, just remember that it is called a static characteristic. Okay, so this is first important property of an op-amp. Now I'm going to discuss about, say, another property, say property number 2. Okay, so this property is as follows. So this is okay, so this is how we draw an op-amp. It has one output, two inputs, one denoted as plus, another denoted as minus. It has two power supplies. Power supplies are drawn like this. One of them is positive, plus V supply, another is minus V supply. Okay, and I can connect these two inputs to some source of voltages, and then the output depends on the difference between these two voltages. Now the second important property of the op-amp is that no matter whatever this input voltage is, so this I called as Vn, no matter whatever the value of Vn is, positive, negative, however large, however small, doesn't matter, no current goes inside the op-amp. This current is 0. Okay, no current can even come out through this terminal. Nothing goes in, nothing comes out. Nothing goes in, nothing comes out. No matter how large, how small, or positive or negative, whatever voltage you give here. Same for this terminal. Whatever is the value of Vp, no current goes in, no current comes out. Okay, so no current passes inside the triangle or comes out of this triangle. So this property, let me write it that no current goes into or comes out from the input terminals. Yeah, right. So this can also be said equivalently that the input impedance of an op-amp is equal to infinity. Yeah. So what do I mean by that? So the voltage, no matter whatever the voltage is, the current is 0, right? So the voltage by current is voltage by 0, because the current is 0, is equal to infinite. So that's what is meant by the statement that input impedance is infinite for both these input terminals. No current goes in, no current comes out. This is very, very important property of an op-amp that you must know, must remember. Now the third property, which is also very important, is as follows. Property 3. Okay, let's first discuss it and then I'll write it. Okay, suppose I give this equal to 12 volt and this equal to minus 12 volt. These are the supply voltages. And now suppose the Vp, this value is equal to say 3 volt and this equal to 2 volt, right? So what will be the output? Think of it. Take a pause and think of it. What will be the output value? See, this is 3 volt, this is 2 volt. So this is at higher potential than this one. So the positive one is at higher potential. So the output will be equal to the positive supply voltage. So the output in this case will be 12 volt. Now if I leave this terminal open as it is, then nothing happens. But what I can do, I can say connect a piece of resistance and the other terminal is grounded, right? So this is grounded, means 0 volt. This is at 12 volt. So what will happen? Some current will flow. Okay, and now, okay, so then it's acting like a battery, like a cell, right? So if you connect a resistance, you get a 12 volt. It acts like a 12 volt battery and some current flows through it. Now if we consider a battery, a normal battery, so that which we draw like this, say a 1.5 volt battery, a normal pencil battery, a AAA battery, and if we measure the potential across these two terminals with a potentiometer, we will see that the voltage is 1.5 volt. Now if I connect a piece of resistance like this, then definitely some current will flow. Say this, if this is 1 ohm, then 1.5 ampere current will flow. And at this point, if I again measure the potential between these two terminals, I will see that the potential difference is not 1.5 volt, but it's lower than that. It can be 1 volt, 1.2 volt, maybe even lower, but it's lower than 1.5 volt. And it depends on how much current is flowing through this resistance. Why is that so? That's because we know that the cell has some internal resistance, which let me write it as Ri. So it has some internal resistance, therefore when some current flows through it, then it causes some voltage to drop, and therefore the voltage when we measure here is lower than 1.5 volt when some current is flowing, right? But in case of an op-amp, if you connect a resistance like this, then this voltage is never dropped, because the internal resistance in this op-amp, if you think of an internal resistance here inside, that's 0. So if you take any amount of current, ideally the voltage will stay at 12 volt. Practically it may drop slightly, but ideally it will stay at 12 volt. Theoretically it will still stay at 12 volt and will never become 11 volt or even 11.5 volt or even 11.8 volt. It will never become so. It will stay at 12 volt. It will never become 11.5. Okay, so this is a third important property. So let me write it as output voltage never drops, never falls down, no matter whatever current is drawn, right? And this is equivalent of saying that the internal resistance at the output terminal, or in short the output impedance, that is internal impedance of output terminal, is 0. If that is 0, like here, if this is 0, then no matter whatever current you draw, voltage won't drop. So this is equivalent of saying the output impedance or internal impedance of the output terminal, impedance, is equal to 0. Right? So this is the third important property you must know, you must remember about the op-amp.